This research is to determine the extra heat loss in a thermos due to its lid. A while ago, I bought a thermos at a store, and it was a pretty cheap thermos compared to other ones that were a lot more expensive. With the expensive thermoses, you could assume that they would do a really good job with their performance in keeping heat trapped in. Um, I assumed that since this was a cheaper one that it wouldn't be able to do as well. But the claim on the thermos was that it would be able to keep the liquids inside cold all day or hot all day long. And this was a pretty impressive claim. The East Rim brand water bottle claimed to keep liquids hot or cold all day long. And I believed that it would keep liquids cold all day long, because if you were to put ice cubes in the thermos, then it would have to take quite a bit of the time to undergo a phase change before it started to warm up. But for it to be hot all day long was a completely different assumption. Going into this project, assuming that by all day it means 8 hours long in time, and keeping the liquid hot as being above a temperature of approximately 50 degrees Celsius. These parameters are what I decided to go with. And then also in the analysis, are the two sections of the thermos that we would take into account, and that's the body of the thermos and the lid of the thermos, which have completely different geometries, as well as materials and properties, which are probably going to give much different results as far as heat transfer. So in this experiment, as we look into the body of the thermos, it is vacuum insulated, which is why they were able to make the claim for it to retain heat for so long, because its only form of heat transfer is radiation heat transfer, because the vacuum insulation doesn't contain any medium for the heat to conduct through. Therefore, it takes much longer. But also in this experiment includes the lid, which does allow for conduction to occur, which allows the heat to escape the thermos much more quickly. Assuming a scenario where the thermos is filled with hot water in a cold environment, we will have relatively cold outer surface of the body of the thermos, especially compared to the lid, which is going to be warmer than the surface because of the increased heat transfer at that point. So continuing on with the experiment, the thermos was filled with water at 100 degrees Celsius and placed in an atmosphere of 2.5 degrees Celsius for it to cool with respect to time. And the data in this table below shows the time frame. The experiment went on for a little over 22 hours, where at certain points in time the water was measured for its temperature. So you can see here the increments in time aren't all uniform as the 24-hour time went by, and so it's a little difficult to see any trends as far as linearity, non-linearity, things like that. And so we'll get to that in the next slide. We'll look at a graph to see those. But then also with the given data of the temperatures, we're able to find the heat loss over time in watts, as shown in the third column here. Transient heat transfer was analyzed as we took the data that was found and put them into graphs. The two graphs we show here are temperature versus time and heat loss versus time. In temperature versus time, we can see that it's obviously not linear. Starting at 100 degrees Celsius at 0 seconds, we see that the time decreases very quickly at the beginning, and as time goes on, the decrease in temperature slows down. And if we look at the heat loss versus time, we can see the same results, where at the beginning there's a big loss in heat transfer, and as time goes on, the heat loss, the change in heat loss over time gets smaller and smaller. This is interesting because when you think about it, the rate of heat loss depends on the temperature differences of the outer surface of the thermos and the surrounding temperatures. And so as the water inside the thermos gets colder and colder, the outer surfaces are also going to get colder, which results in the temperature difference of the surface and the surroundings getting smaller. And because that happens, the heat loss is also going to get smaller. And so because of the complex geometry of this part, and because there's so much change in this transient heat transfer problem with respect to time, we went further into the analysis by simulating this heat transfer in the thermos with engineering software. So an FEA analysis was performed to compare heat loss from conduction versus radiation. Here we're able to see more clearly how conduction plays such a big role, even though it pertains to the smaller surface area here. This analysis included the inner radiation, convection on the outside of the surface as well, which included the free convection from the air, and radiation based on the differences in temperature from the surroundings and the surface of the thermos. It was calculated that about 2.8 watts of heat is leaving due to radiation on the sides, and 12 watts is leaving from the lid, resulting in about 80% of the heat loss coming